Hi, we are from Group 11 and my name is Lee Keng Ed, and me and my teammates which is Wong Chi Hee and Chong Xian Wei, we are designing for a 4-bit booth multiplier design. Okay, next. Okay, so I will be introducing the booth multiplier. What is a booth multiplier? So, okay, the problem statement that booth multiplier can solve is design an efficient sign binary multiplier use the booth operator with FSMD architecture to do the job. And the objective is we implement a 4-bit booth multiplier in Verilog verified using the quarter simulation and justify the FSMD approach in this assignment. Right. In the design specification, we use the pin A and B, and the output we are using 4 bits, right? So when it multiplies, we'll get it back 8 bits, and we have 4 clock cycles to show the result after when two things multiply together. And thank you. Next. Oh, okay. So what is CU and DU? So in this part, we are using FSMD. FSMD inside included the CU and DU inside the code. So what is a CU? You can see here. The CU is a control unit. It's the brain of the FSM, and it monitors the status of signal based on the commands add, shift, or like that. And data path is the muscle, right? Hardware responsible for storage and manipulation. Contain the register for the ABC and the 4-bit combination adder and subtractor inside it. That is the DU. Okay, here is why we stated that we use FSMD, not FSM plus D. So FSM plus D is basically much complex in terms of complexity, and the structure FSMD is very simple as everything is implemented inside the same code, right? FSM plus D is more way harder, okay, and the routing less routing best for both multiplier, and FSM plus D is better for CPU design as our topic is quite easy, so we choose FSMD. Thank you. Next, I will pass it to my next teammate to present.
I'm Wong Chi Hee, and I will be talking about the internal data path. First, we have register A and register B for 4 bits to hold the first and second value. Next, we have register C. Register C will be the upper 4 bits for the final product, and it will hold for the value updated in each operation of the code. Next, we have implicit bit B minus 1, which will be updated for each loop with the B0, and implicit bit will be determined for the addition, subtraction, or the no operation done for the math code. Next, we have a loop counter. The loop counter is used to determine there will be 4 loops done to obtain for the 8-bit final product. Okay, next is the FSM execution sequence. We have 4 state, then I will briefly explain about them. For state 0, is the state that the value loads into the code. Okay, then in state 1 is where the math operations occurs, determined from state 0. We have addition, subtraction, and no operations. Then we move to the shift state. We will have arithmetic shift right for C and B, and also B minus. Then when the loop is we have 4 loops done, we will move to state 3. Then the upper 4 bits will be C and the lower 4 bits will be B. Okay, now I will talk about the control state table. Okay, for state 0, when only start equals to 1, the values will load into A and B. Then 0 will be load into C, B minus 1, and also loop. Next will be the state 1, okay, the maths operation. So when B0 and B minus 1 equals to 0, 1, C, the operation done is addition. Then when B0 and B minus 1 is 1, 0, the subtraction will be operated. Okay, so when 0, 0 or 1, 1, C will remains the same. Then move to the state 2, the shift state. Okay, so when loop is lesser than 3, C will be the top bit of C and also the bit of 3 to 1 in the last C. So B will updated with C0 as the most significant bit and B following with B3 to 1 bit. Okay. Then also we have B minus will be B0 bit. Then also we'll update uh, 1 into the loop. Then it will move to state 1 again, then move to state 2 again. Okay, when the loop reaches 3, because 0, 1, 2, 3, the 3 will be updated in the next loop and not the current loop. So we are only reach until 3 for 4 loops. Then it will only move to the third state. Okay, the third state will be setting our final output to be upper 4 bits to be C and the lower 4 bits to be B. Okay, these are the state diagram and the ASM chart for a better understanding. So when in state 0, okay, when start is equal to 1, we will move to state 1 to perform the math operation. Then it will no need any condition, then we'll move to state 2 for the shift. So when loop is lesser than 3, we'll move back to state 1. Okay. Then okay, when loop is equals to 3, then we'll have our output ready.
Hi, I am Chung Xian Wei. I am going to talk about our synthesis result. So the diagram on our left-hand side show that our code successfully run in our quarter spine with zero error. The diagram for the right-hand side show our synthesis RTL schematic. Since we are using the SSND, so that the CO and DO are all in the one block. It does not separately. So next is our simulation result. First, we test for two positive values. We use 3 times 2, we get 6. Next, we test for positive times negative value. We use 3 times negative 2, we get negative 6. The third one, we use negative value times positive value. Negative 3 times 2, we get negative 6 also. After that, we try to multiply two negative values. We try to use negative 3 times negative 2, then we get a positive 6. Then we try the 0 multiplier. We use 5 times 0, then we get 0. But lastly, when we try to use maximum negative value limit with negative x times negative x, we get the result of negative 64 instead of positive 64. This is because the 4-bit accumulator cannot represent the positive x. It will overflow, so it will present negative value for 64. So let me to do the summary for our design. Our design successfully multiplied the signed 4-bit two complement numbers to having a correct functional operation. We pass all the normal cases for positive, negative, and zero input. For FSMD architecture, we design to have CO and DO integrate in one module, so that if we are having the simple implementation with lower hardware complexity, it also suitable for sequential post multiplication. However, we having the hardware limitation in the maximum negative value test case, we produce a result of negative 64 instead of positive 64. This is because the 4-bit accumulator cannot represent the positive x, so it will causing the overflow. This reflects the limitation of strict 4-bit implementation rather than an error in algorithm.